All right, we're just going to take it up a notch here. So, momentum notes, exclamation point. Remember, momentum, if you see a collision on the AP Physics test, odds are you're going to be using momentum. And we haven't even done any examples yet. We're just kind of doing the theoretical note part right now, but you'll see it in a few minutes here. So, I had to white out a whole bunch of stuff. No, I just realized my paper stuck to it because this random assignment there that I wrote down. So, we're going to talk through some old knowledge with some new knowledge. So, we think back. We know Newton's second law is force equals mass times acceleration. Remember, force is a vector, acceleration is a vector. And don't worry about those arrows yet, they're gonna go somewhere. And we know now from the last video that momentum equals mass times velocity. I'm gonna show you how these relationships to these equations are very similar to each other and they kind of work kind of neat together. So let's take Newton's second law here and let's develop a little bit more. The m is just gonna come down. But remember, what's the definition of acceleration? You're changing your velocity with respect to time. So you call it dv dt if you're talking calculus stuff, or you can call it delta v over delta t. So I just wrote that real quick. I said, okay, let's call acceleration v final minus v initial divided by your change in time. Okay, so we had that, and then I just brought the m down just for fun. And so now I have this equation, and I pre-wrote these notes and I have like scratches or crossouts, but now I'm going to distribute the mass through. So just like that. So you're going to do that and then hit pause, and if you need to come back, but distribute the mass through. And you're going to see this right here. I'm going to cover this up with my hand. mv final, boom, minus mv initial divided by the change in time. You're like, whoa, whoa, whoa. This is my old knowledge, and that kind of ties into something that looks kind of familiar over there. So when you see mv, your brain should go ding, ding, ding. mv, that is momentum, and since it's v final, that's the object's final momentum at the end of experiencing a certain force, minus mv initial here, so that's your final momentum, minus your initial momentum, because m times v is momentum. So the time delta t just comes along for the ride. So you're going to write it as p final minus p initial. And you know, if you ever take something at the end minus what it was at the beginning, I should have vector signs over this, but don't judge me, okay? I drop them all the time. Force is a vector still, always and forever. So that's delta p. So you write that as delta p over delta t. And this is the big takeaway. If you ever apply a force for a certain amount of time, you are going to an outside force to your system for a certain amount of time, you're going to change an object's momentum, okay? And instead of writing it delta p over delta t, you could write it dp dt. This is a very important equation. You can write it as the fundamental definition, Newton's second law. When he actually wrote his second law in his, I think it was his Principia Mathematica, I think that was the first book he wrote it in, he said, F equals dp dt. He said, if you apply an external force to a system, you are going to change that object's momentum with respect to time. Okay? So we're going to talk more about this. If you want to write it the calculus way, forces are dp dt. That comes from, that's the same as writing F equals ma. So Newton's second law can be written this way or that way in terms of momentum. Same difference. Okay? And if you want to write it the non-calculus way, which actually on our AP test, they do write it this way. They pause it right here. They said force equals delta P over delta T, and they just kind of rearrange it. They say, oh, that means delta P equals force times time. I want you to write the non-calculus way as well, because it's really important, because here's how you read this. If you have an external force to your system, and you apply it for a certain amount of time, you will change the momentum of that system, okay? And you're like, I thought you said you couldn't change, like pi equals pf, momentum's conserved. Absolutely 100%. If for a closed system, momentum initial equals momentum final. But if you ever have an external force acting for a certain amount of time, you will change the momentum of that system. And I just picture your alarm goes off and you're at rest in your bed, you don't want to get up, and you're like, pi equals pf, I'm at rest, I'm staying at rest. And then that force, your parent, guardian, mom, dad, brother, sister, uncle, whatever comes in and says, get out of bed. They're an external force, and they keep saying, get out of bed. And they do it for a certain amount of time, and they push on you. Well, that will change the momentum of your system. You will be inertia in motion because you probably get the class, okay? And so F times T equals delta P. And they call this change momentum, they give a very special name. They call that an impulse. So we have that when you change an object's momentum, that is an impulse on your system. Important, that's a derivation of where this formula comes from based on momentum. If you have it memorized, great. If you want to reason it through, that's even better, okay? Don't mind my crossouts over here. I just don't want to rewrite my notes because I thought they were pretty neat already. Now, you might be saying, Laurent, that sounds kind of familiar to what we've done in the past. Well, let's just think about this. If you made a graph of the force you applied for a certain amount of time, so a force versus time graph, F versus T. force versus time graph, a Newton times a second, a Newton times a second. If you take the area of that graph, that will give you how much impulse was imparted on your system. You're like, that sounds kind of familiar, but how does it relate to my old knowledge? Well, here's the deal. I'm going to try to put them up side by side. Back in the day, if you had outside work acting on your system, force should have vector symbols. Put no, time's not a vector. From vector symbol. This right here would be force versus displacement, delta x here. Just like that. So you're like, whoa, 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 this looks kind of familiar. If you have an outside force acting for a certain displacement, in meters, the area gives you work. That's very similar to that force acting for a certain time. That gives you impulse. So the reason I wanted to write these side by side going into the new momentum unit, it's not like we're going to learn a whole bunch of brand new ways of doing business. We're going to do some similar things like EF and EI like we did in energy unit. We're going to do PF and PI and stuff like that for momentum. And you're like, well, Laurent, yeah, if I apply a force for a delta x, and let's just say the cosine was 0, they're aligned, these two vectors. If you apply a force for a certain displacement, that's work. If you apply force for a certain time, that's impulse. I wanted you to see them side by side because this is what we've done and this is what we're gonna do. So if the old stuff, you're like, yeah, that looks familiar, that makes my heart happy, great. I'm gonna try to make your heart happy with the new stuff too, okay? And just one little hint, remember I said you could always do EF minus EI equals 0 unless there was an outside force acting on your system doing work? Remember I said you could say, hey, you could, EF minus EI equals 0 unless it's equal to work, like friction, or maybe somebody's pushing you. The same is true for momentum. You can take P final minus P initial, and it should be equal to 0. But if you ever have an external force acting on your system, it'll be equal to the impulse right there, because you're applying a force for a certain amount of time. And if you're like, Laurent, I'm not getting this, take down the notes, get them in your brain, and we're going to do some examples. It'll make sense. Okay, so I'm going to hit pause right here. That was just a little derivation, how F equals ma Newton's second law ties into our new knowledge. And momentum also ties back to energy, and that's what I wanted you to see in this short little video. Okay, so if this was confusing, you could actually watch this a little bit later, and it might make more sense after you do some examples.